Welcome to the August edition of Midday Science Cafe, where UC Berkeley and Lawrence Berkeley National Labs join together. We have the pleasure of introducing Sean Lubner from Berkeley Lab and Lilia Gia, both from UC Berkeley. And this is an extremely timely conversation, I think, given what's going on in California with the power outages and such. The title of the presentation today is Energy Storage Solutions for a Clean Energy Future. So I will give you a little bit well, maybe what I'll do first is talk about what Science at Cal is, which is the program that I run at UC Berkeley. We create opportunities for Berkeley scientists to engage with the public in myriad ways through lectures and science cafes, festivals, and more. I hope that you join us in the future when we're back live and in person. But until then, we are going to be hosting programs online. And if you would like to join our listserv to learn more about all of our programs, please visit us at scienceatcal.berkeley.edu or email us at scienceatcal@berkeley.edu. Of course, you can always follow us too on all of our social media accounts, Facebook, Twitter, and Instagram at Science at Cal. So before I hand things over to my colleague at Berkeley Lab, I will just describe how the presentation will go today. We will first start with Sean Lubner to talk about his research. Then Jen will go through some questions with Sean. Then she'll hand things over to Lilia Gia, and we will go through some questions with her. So there's so many opportunities to answer questions. I hope that you continue throughout the entire presentation to be asking questions within the Q&A. We'll have plenty of opportunities to talk with our scientists at the end of Lilia's presentation, where we join together and again have a really lively conversation about energy storage. I want to remind you that our presentation will also be recorded. So if you'd like to share our presentation after or watch it again, you're more than willing to do so by visiting our social media channels, and we'll send the video out at the end of the presentation, likely tomorrow. So I am going to now hand things over to, again, my colleague Jen Tang at Berkeley Lab.
Thanks so much, Dee. Hi, folks. My name is Jen Tang, and I'm the manager for Federal and Community Relations at Berkeley Lab. And for those who might not be aware, Berkeley Lab is one of 17 U.S. Department of Energy national laboratories across the country that are tackling the critical scientific challenges of our time. Berkeley Lab is supported by DOE through its Office of Science, and we're managed by the University of California. Since our founding nearly 90 years ago by a UC Berkeley physics professor named Ernest Orlando Lawrence, Berkeley Lab has been dedicated to advancing the scope of human knowledge and seeking science solutions to some of the greatest problems facing humankind. Today, Berkeley Lab researchers develop sustainable energy and environmental solutions, create useful new materials, advance the frontiers of computing, and probe the mysteries of life, matter, and the universe. All of the research we conduct at the lab is unclassified. Our main campus is nestled in the Berkeley Hills northeast of the UC Berkeley campus, and we employ about 4,000 people, 1,700 of whom are scientists, engineers, and faculty members. More than 500 of our employees are undergraduate and graduate students. These are scientists who are just beginning their research journey. Berkeley Lab's proximity to Cal and our close ties to the UC system create a unique and synergistic environment for scientific discovery. Many members of our community are affiliated with one of the UC campuses, either as students, postdocs, or professors with joint appointments to conduct research at the lab. As you can imagine, Berkeley Lab's relationship with UC Berkeley is particularly close, and our institutions have joined forces to advance science on a number of different frontiers. One of the main motivations for creating this Midday Science Cafe series is to share with you examples of really compelling and complementary scientific research from both of our institutions. We hope you enjoy today's presentation and look forward to highlighting other science stories in the months ahead. And now it's my pleasure to introduce our first speaker, Dr. Sean Lubner. Sean is a research scientist and Seaborg Fellow in the lab's energy technologies area, where he specializes in modeling and measurement of nano to macro scale heat transfer and energy conversion. He's worked on a variety of systems, including energy storage, biomedical devices, water desalination, electronic materials characterization, and solid-state energy conversion. Before becoming a staff scientist at the lab, he spent 2 years as a postdoc, where he was awarded an early career lab-directed R&D grant. He earned his bachelor's degrees in applied physics and mechanical engineering from Carnegie Mellon University, and his PhD in mechanical engineering from UC Berkeley, where he was a National Science Foundation Fellow. Go Bears! Sean, let me turn it over to you.
Great, thanks, Jen. All right, so today I'm going to be talking about the need for energy storage. And to spoil the ending, it's the only way that we can make the switch to all renewable energy. So let's start with, why do we want to switch to renewable energy? Well, one big reason is to mitigate climate change. Renewable energy can provide carbon neutral forms of energy. And unfortunately, our CO2 levels are already higher than they've been in at least the past 800,000 years, which has included multiple ice ages. But there are also other big driving factors for making the switch. Another big reason is to realize energy independence and national security. So the US imports 500,000 barrels of oil and 35 million pounds of coal per day. And those fossil fuels are subject to large price fluctuations, as you can see in this historical data. So if we can switch to all renewable energy, then we can protect the economy against this price volatility and be independent from other countries for our energy. And then another big reason is just that extracting fossil fuels requires increasingly extreme approaches. So here I'm just showing a few of those possible approaches. But you can see that these are not sustainable, and it's only going to get harder and more expensive to keep pulling fossil fuels out of the ground. We really need to make the switch to the renewable energy sooner or later, and so we might as well try to do it sooner. So in theory, we actually already have sufficiently advanced solar and wind technology right now to provide all the renewable energy we need. So why haven't we made the switch yet? Well, one big problem is that renewable energy is not dispatchable on demand. You see, fossil fuel kind of has energy storage built in. It just sits there waiting until you need it, and then you burn it. However, renewable energy is intermittent. You get it when you get it. You have to wait until the sun is shining to get solar energy. You have to wait until the wind is blowing to get wind power. You can't just dispatch it whenever you want it. So one very striking example of this is to look at the electricity prices in Iowa, where they have a lot of wind power on the grid. So this plot is showing historical data about 2 years worth of electricity prices in Iowa when they've had a lot of wind on the grid. And what you can see is it's very volatile. It fluctuates quite a bit. The price goes up and down. If there's very little wind blowing, but there's a big demand for power, then the price of electricity spikes up because the demand is much bigger than the supply. Conversely, if there's a huge gust of wind that comes and then you have a lot of wind on the grid, but there's not much demand for that power, then the electricity price crashes because there's an oversupply. And it can crash so severely that the price actually goes negative. As you can see here, this black line shows the 0 point, and sometimes the electricity producer is actually paying the grid to take the electricity off their hand because they don't have energy storage. And so they don't have a way to hold on to this surplus of power until it is needed. And the same thing happens with solar power. You actually see in California, you can get negative electricity prices on particularly sunny days. And this is already a problem now. In fact, this data is over 5 years old. And so if we try to add more renewable energy to the grid, even though we have the technology to do that, we're just going to make this problem worse unless we add that with energy storage. So we really need this storage to make renewable energy dispatchable. And all of this, so far, this is just talking about electricity, which is actually only a minor portion of how we use, a minority portion of how we use our energy. To really understand how we use all of our energy, we want to look at the big picture. So this is a bit of a busy graph. You don't need to absorb all the details, and I'll walk you through it, don't worry. But it's a high-level summary of how our country uses all of its energy. So on the far left are all the different primary energy sources that we have. I know the text is a little small, so I'll just quickly read through them. So starting at the top, we've got solar, nuclear, hydro, wind, geothermal, natural gas is a big one. Then we've got coal, biomass, and then petroleum is the other really big source. And then this chart shows where the thickness of the line is proportional to how much energy there is, where it all goes. So as all this energy flows to the right, it ends up in different final end use cases, and that's what those pink boxes are. And so just reading through those quickly, it's residential, commercial, industrial, or transportation is a big one. And what I want you to notice is that electricity, what we've been talking about, is just this relatively thin orange line at the top. Even though that's how most people think about energy, is in the form of electricity, because that's how we're used to interacting with it. it's not the primary way that we use energy. So if I blank out electricity, everything else that's left on this graph is heat. And so we are actually a heat nation. And this heat also needs dispatchability. You see, heat is primarily used by industry for manufacturing processes. And they need to run these processes efficiently 24/7, reliably without interruptions. And so they need a dispatchable form of energy. They cannot switch over to renewables until it's dispatchable. So to emphasize that, I'm now going to blank out the remaining renewable energy sources on the plot. And you can see that not much changed. Almost all of the energy that we get for industry is from fossil fuels because that can be dispatched when we need it. So we really need a way to store renewable energy so that we can control when we dispatch it if we ever want to switch the entire country over to renewable energy. Okay, so I'm now going to zoom out and I'm going to cluster these end uses into two general categories. One is going to be heat and electricity. So this is for things like manufacturing, building lighting, HVAC, and so on. The other cluster is going to be transportation, and that actually gets its own section because it's a pretty big one. And these are things like planes, trains, and automobiles. And this is both the transportation of people as well as the transportation of goods. And now in the remainder of this talk, I'm going to take a quick look at research in 3 different technologies that my colleagues and I are looking into to help for these different applications. So the first will be lithium-ion batteries for transportation. Then we'll look at thermal energy storage, and then we'll finish with a quick look at optical control. Great, so let's first talk about transportation. When people think about making transportation green and having it powered by renewable energy, they think of electric vehicles. And electric vehicles require batteries. However, other than price, one of the major complaints preventing the widespread adoption of electric vehicles is slow recharge times. You cannot right now recharge electric vehicles nearly as quickly as you can refuel gasoline cars. And this greatly lowers their practicality. So you might ask, well, why can't you just charge a battery faster, just pump more current into it? Well, there are 2 main problems with that. The first is that you'll cause lithium plating. And this is something that essentially causes irreversible capacity loss of the battery. So you definitely don't want to do that. The second big problem is that the battery will overheat, which will also cause capacity loss, but can then also cause things like fire, explosions, and much worse bad things to happen. So to understand why this happens, we need to understand how heat moves inside of batteries. So if you haven't seen it before, this is what the inside of a battery looks like. It's this tightly coiled up, multi-layered structure. In the next talk, Lilia is going to explain more about how batteries work. But for now, all you need to know is that it's got this multi-layered structures of anodes, cathodes, and separators repeated many, many times and rolled up. So our goal here is to help the heat get out quicker, to really help that heat move through all these different layers so that you can charge your battery quicker. But the problem is that the heat leaves slower than we expect, and we don't really know why. So to address this, my colleagues and I developed some new sensors to try to map thermal transport inside batteries. So this is a picture just so you can see what they look like. What you're looking at is one small test cathode before it's being inserted into the battery. And you can see individual sensors, 2 of them actually wired up, ready for experiments. And what these sensors do is they emit thermal waves into the battery. And you can think of it kind of like a thermal sonar. So this lets us see what the heat sees. Even without sticking something all the way inside the battery, we can probe thermally to see what's going on. So we wire up these sensors and we put them inside a test battery. It's called a pouch cell, which you can see here on the right. And what we discovered is that the heat gets stuck in between the different layers of the battery. So this bar on the left is showing schematically, proportional to the height of each color, how much each individual component of the battery is responsible for blocking the heat, for preventing that heat from being able to escape from the batteries. And what you can see is that actually the majority of the thermal resistance does not come from any one component of the battery, but it comes from the interface between those layers. So now that we understand this, we can better focus our research efforts to improve the battery recharge time. Okay, so that's great for transportation. But again, that accounts for about 1/3 of how we use energy as a country. The rest of our energy is used for heat and electricity. It's this larger category I've shown at the top. And unfortunately, current battery technology is too expensive to store energy on the much larger scales required for these kinds of heat and electrical grid storage applications. However, thermal energy has the potential to be a much cheaper and more economical approach for very large scale energy storage. So this is another area that my lab is looking into. So the idea here is that we want to look at storing energy as high temperature heat for large scale energy storage applications. You do this by taking a very cheap material, right? That's one of the big advantages of this approach. It can be really cheap. It can be graphite, clay, it can even literally be dirt and rock. And you just take that material and you heat it up to a very high temperature. You can do this by taking cheap electricity. Remember earlier, I was showing you how sometimes the price of electricity crashes because all this intermittent renewable energy dumps electricity on the grid, maybe not when we need it. Well, now we can take that electricity and use resistive heating to turn it into heat. And we can take that from any source, right? This can come from wind, solar, nuclear, could even come from fossil fuels. And then we can just hold on to that energy for a very long time as heat. And then we can dispatch it later on demand. So the other advantage of storing it as heat is that we can dispatch it again as heat. And as you might remember from the previous plots, a lot of applications of energy are just heat. Industry sometimes just wants direct heat to manufacture cement, glass, steel, those kinds of things. And so that's an advantage of storing energy as heat. But we can also then use a heat engine to convert that heat back into electricity if we need electricity. And it turns out that heat is a surprisingly compact way of storing energy. In fact, 1 cubic meter of hot graphite can store enough energy to power a house for a month. And we think that this form of energy storage can also be cheap, scalable, safe, and you can deploy it pretty much anywhere. And I can talk more about that later in the Q&A. Okay, so finally, I'll finish with a quick word on optical control. So converting energy to and from heat often requires controlling photons. If you think about it, if you concentrate many photons in one place, that spot tends to get very hot. Conversely, if you make things very hot, they tend to glow and emit photons. And this interplay between materials and photons can be summarized with this plot that I'm showing at the bottom. So what this plot is showing is the efficiency with which a material or structures can absorb and emit photons as a function of the wavelength of that photon. And so what we're trying to do in my lab is design better materials and structures to control how materials interact with light. So basically design this plot to be what we want it to maximize the energy efficiency. So we've been using some machine learning approaches to design optical coatings to predict these properties. So here I'm showing you a bunch of plots. Each little plot is the same as the one from the previous slide. So I'm showing you the efficiency with which it can absorb or emit photons as a function of the photon wavelength. But now I'm showing it for a bunch of different designs. We've got different materials, so gold, glass, silicon nitride. And we've also got particles of different size and different shape. And you can imagine you can combine them together in different ways. If you look closely, each plot actually has a black line. And that black line is the ground truth of what the optical properties really are for that structure. And then the colored line superposed on top of that is the prediction of our trained machine learning algorithm on what it thinks the optical properties should be. And as you can see, it's starting to get very accurate at understanding the physics. And we're now even starting to turn this around so that we can tell the algorithm what optical properties we want. And in response, it will tell us how to design a structure or a device to produce those optical properties. Okay, so I've only touched on a couple forms of energy storage here, but there are many, many more. And there's no silver bullet. In the end, we're ultimately going to have to combine many different approaches for different situations to realize a fully renewable energy future. And with that, I'd be happy to take any questions.
Thanks so much, Sean, for that great presentation. We do have a couple of questions for you before we turn it over to Lilia. So the first question we received from one of our attendees is around pumped water energy storage. He's been reading a lot about a proposed pumped water energy storage project near the Grand Canyon. And he was wondering, can you compare the efficiency of pumped water energy storage to battery storage? And a follow-up question is, are there any ideal locations for pumped water energy storage?
Sure, great questions. So in general, if you're trying to assess different energy storage technologies, one metric is efficiency, but another important metric is cost. So I don't know the exact numbers for pumped hydro. I think it's fairly high efficiency. I would guess around 80%, which is not going to be as high as batteries, which can be over 90% efficiency. And both of those are much higher than, say, thermal energy storage, which is around 50% efficiency. However, pumped hydro can be a lot cheaper than batteries. And so the lower efficiency can be offset by the cost. And conversely, thermal energy storage can be much, much cheaper than either of those. So even though it's the lowest efficiency, it's much, much cheaper. So in some situations, it's better. But if you're trying to go for pumped hydro, one of the constraints there is geographically, you need a large elevation separation, right? You need a hill, essentially, that you can pump the water up, that you can let it flow back down. And so that means that some places are ideal for it, but some places you just cannot use it.
Got it. Thanks for that answer. One other question we'll ask, and we'll save the others we're getting for after after both of you have presented. You talked a little bit about the safety concerns around EV batteries when they're charged too quickly. One question from an attendee has asked, what safety protocols are applicable to the location and design of large utility and industrial-sized lithium-ion battery storage facilities? I think the concern there is around fire and explosion hazards, maybe toxicity issues regarding the gases that might be released during a fire, and the general life cycle of toxicity and waste issues for large grid scale batteries.
Sure. So if you mean batteries in the sense of electrochemical batteries, the risks kind of scale directly with their size. All batteries, whether it's in your cell phone or whether it's a Tesla Powerwall, I think that's the new product to power a house, risk overheating and thermal runaway. But we have pretty advanced battery thermal management systems that we're trying to put in place. And as I said, we're trying to improve the materials of batteries so that they can dissipate heat quicker. However, if you mean battery in the general sense of energy storage, I believe that for very large grid scale energy storage, we probably won't see electrochemical batteries, but we'll see things like thermal energy storage. And there, actually, the safety is much higher. People think of it as being very risky because it's very hot. But essentially, heat cannot explode because it's already heat. It's actually the only form of energy that you can have where it cannot spontaneously turn into heat, which is what an explosion is, because it's already heat. So it's one of the most stable and safe ways to store energy. Really, the biggest safety risk there is if, say, your water cooling line breaks and you get water injected in, you could get a steam explosion. But barring that, the other worst case scenario is that the heat slowly diffuses into the ambient over time. So we think it should be quite deployable in that sense.
Thank you, Sean, for those answers to those questions. And thanks to the audience for submitting a number of questions. We've got a lot. We'll get to them after the presentations. But for now, let me say thanks to Sean for that presentation. And I'm going to turn it over to Dee, who's going to introduce our next speaker, Lilia Gia.
Excellent, great. That was so wonderful, Sean. I hope to now hear from you, Lilia Gia. She is a postdoc scholar in the Department of Chemistry at the University of California, Berkeley. Since we already went there, I will say go Bears. She is currently working with Professor Kwabena Bediako to create new two-dimensional layered materials with potential applications in next-generation energy storage devices and computational schemes. She earned a PhD in chemistry from MIT, where she worked on electrical conductive porous framework materials while supported by the National Science Foundation Graduate Research Fellowship. So we have two NSF graduate fellows today, which is incredible. She did that work at MIT as a also a presidential fellow, and she has her degree in chemistry from Princeton University. She has also served on the leadership board of the MIT Science Policy Initiative and worked as a technology analyst for the energy storage industry. So she's been in a lot of different spaces, it sounds like. She is passionate about catalyzing connections between scientists and society, which is what we are doing here today. So we are so excited to see you, Lilia, and to have you join us. So I will go ahead and let you take it away.
Thank you so much, Dee, for that kind introduction. I'm really excited to be here today. And I'll be talking about some of the work that we're doing in the Bediako Lab in the chemistry department at UC Berkeley around trying to design materials that could one day be used in more efficient, smaller, and more powerful batteries. So as Sean has explained very clearly in his talk already, there's a lot of reasons why we would want to move eventually to having more renewable sources of energy on the grid. But one of the challenges with integrating renewable energy into the power grid is that these are intermittent sources. So when the sun isn't shining or the wind isn't blowing, the power that they put out is inconsistent. So if we have energy storage on the grid that can either absorb power when there's an excess or put out power when there's not enough to meet the demands, then we can ensure that there's a constant power supply, or the power that's needed in our homes, in our offices, in industrial settings is sufficient for them to operate. So there are several different types of energy storage that are relevant and used widely today. So hydroelectric and thermal storage and electrochemical storage, as Sean has already given an overview. And so to give you a sense of the distribution of energy storage projects among these different technologies in the United States. So if we look at the rated power here, we see that pumped hydro makes up a pretty large component if we look at power. But actually, in terms of the number of projects, electrochemical energy storage is a majority. And so one reason for that is that batteries are just, by nature, they are a bit more scalable than these other types of storage. So I'll be focusing on battery technologies today. And there's several different chemistries, different types of batteries that are relevant to energy storage applications on the grid. But the one that I'll talk about most today is lithium-ion batteries. And so these are pretty familiar to all of us, I would say. They are in our phones, in our computers, our personal electronics. And they're also the type of battery that is most common in electric vehicles. And I saw that there was a question earlier about walls, like power walls that you can install in your home that can store, solar energy, for example, if you have a solar panel installation. Those are also usually with lithium-ion batteries. So in addition to these kind of smaller scale applications, they can also be used in larger scale kind of grid storage applications. And so basically every lithium-ion battery has the same components. And the three that I'll talk about today that I think are most important to understanding how these batteries work are the cathode, the anode, and the electrolyte. So the cathode and anode are solid materials that basically store lithium in these batteries, and the electrolyte is a medium that the lithium ions can move through. So when the battery is discharging, which means that it's supplying power to an external device, lithium ions will move from the anode across the electrolyte to the cathode. And simultaneously, as this is happening, electrons will move through this external circuit and supply power. And so when this process is over, all the ions have moved over to the cathode. And if you're charging the battery, this process essentially happens in reverse, where the electrons move through this external circuit in the opposite direction, and your lithium ions are moving from your cathode through your electrolyte to the anode. So you can see that basically how these batteries store electrical energy is by moving lithium back and forth between these two materials, the cathode material and the anode material, and that these materials need to store lithium efficiently for this to happen. So if we take a look at the chemistry and the structures of these materials, so what I mean by that is how the atoms are actually arranged in these solid materials. So this is a picture kind of this arrangement in a typical cathode material, and this is a picture of a typical anode material. And you'll see that they have a lot in common, actually. They're both composed of these horizontal layers of different atoms in these cases, but in both cases, these blue spheres, which are lithium ions, sit between the layers of the other materials. So what is happening when you're charging and discharging your battery is lithium is going in between and out of these layers in both the cathode and the anode materials. And so if we want to make better battery materials, a really important thing we have to do is to study this process kind of on an atomic scale. We have to study the chemistry of how lithium goes into and goes out of these layers. And if we can kind of design an optimal material for this process, then we could make a battery that is more efficient, more powerful, and that would be very useful in many contexts. So the way that our lab is approaching this problem is actually to isolate individual layers of materials that can be found in lithium-ion batteries and studying how lithium goes in at a very microscopic level. So one very common anode material in a lithium-ion battery is graphite. And this is composed of these layers of carbon atoms that are arranged in a honeycomb pattern that are just stacked one on top of the other. And so one layer of graphite is called graphene. And this is the picture if you're kind of looking down in this direction. And so actually, there's a very clever way that you can peel off basically individual layers of graphene from a bulk crystal of graphite. And you can do that using Scotch tape. So if you just take a piece of your graphite or another layered material that has a similar structure even, you can just take a piece of tape and you just pick up a few layers that stick to the tape. And then you can press this tape with your few layers of materials onto a sticky substrate. And then attractive forces between this thin layer of material and the substrate will make it so that you basically stamp exactly one layer of graphene onto your substrate. And so if you do this process twice, you can basically make just an isolated 2 layers of graphene. So it's like a graphene sandwich. And actually by building kind of like a miniature battery, you can study how lithium ions are going into just this one single interface between these 2 layers. And so if we go back to this picture we had before of the lithium ion battery anode material, you can see that it's basically just isolating, one like cross section of this entire anode material. So we're isolating that in this device, and we're looking at exactly how lithium is going into and out of these layers. And so there's actually other materials out there. There's entire families of materials that you can apply this process to that are layered in their structures, and you can use tape or there are other methods as well where you can isolate individual layers. And so just like you can make a sandwich of 2 graphene layers, you can even mix and match these different materials that are made up of different atoms with slightly different structures and have different properties as a result. You can basically stack them like Legos, and you can make these very complex architectures that you can't make using more conventional methods of growing these materials. So this method is just a really powerful way for us to make custom interfaces that can then host lithium more efficiently. And so some of the work in our group actually has shown that if you construct a sandwich of graphene and this different material called MOS2, more lithium goes into this interface between graphene and MOS2 than an interface between 2 layers of MOS2. So that just demonstrates that by mixing and matching these different types of materials, you can tune the efficiency of how lithium ions are going into the space between 2 layers. And so this is one way that in the lab we can try to make better materials for the batteries of the future. And I don't have time to get into it today, but a lot of these materials have many different properties depending on the exact arrangement of the atoms. And there's many other applications in electronics that this strategy could be useful for. So if you are curious in some of those other directions, I encourage you to check out our lab website, bettyakolab.org, and some of the other work that is happening in the chemistry department at Cal, at chemistry.berkeley.edu. And I want to thank Professor Kwabena Bediako and other members of my lab. And I'm happy to take any questions you might have, so please type them into the Q&A box.
Excellent. Thank you so much, Lilia. That was wonderful. So one question that has come in, I know Sean also talked about the scalability, right? Scalability, that's the word, of lithium ion batteries and making them better and faster. And one question that we have is what realistically is a better, faster battery? There must be some point, was it like instantaneously moving the lithium ions over? But what is the time scale that we're actually thinking about currently in terms of making these batteries the best they can be?
Yeah, so you mean in terms of like how long it will take to make that battery? Like,
well, the recharge rate maybe.
Oh, the recharge rate.
Yeah.
Yeah, okay. So there can be a trade-off kind of between basically the recharge rate and the amount of energy that the battery can store, if that makes sense. So basically, and if we look at at the materials level, it just means that materials that lithium can go into and out of really fast might not be the best at storing large amounts of lithium. So it can be challenging to find kind of like the right compromise between those
Right.
aspects. But actually, so I guess
And it
there's
might
like two
depend on,
directions.
yeah, it might depend on the situation you're in too, right?
Yeah, it
What
depends
is
a
being,
lot. Right, definitely. So I think the batteries that are used in consumer electronics, for example, they have slightly different compositions than batteries that are used in grid storage projects, for example. But in terms of making the charge rates really fast, there's actually other technologies that maybe in combination with batteries that could kind of like provide both. So there's a technology called supercapacitor that is really good at charging extremely quickly. So for example, designing like a hybrid technology between batteries and supercapacitors could be one way to kind of get the best of both worlds.
Oh, that's a perfect lead into another question we got from an audience member, which says batteries seem to be basically the same as they have been since Volta first designed them. Has there been any work on something different from the anode separator cathode model, which I feel like you slightly answered that. Is there something more you want to say? Are there different models that scientists are using to create better batteries?
Yeah, absolutely. So lithium ion batteries were discovered, I guess, in the late 80s, like early 90s, and then they became commercialized, I would say, beginning in the 90s and 2000s. And so now, people are definitely looking at new chemistries that can be even better than lithium ion for different applications. So on the grid side of things, so when you have like a big installation, it's not as important to have something that is really compact. So there's basically people looking at replacing lithium with sodium, for example, which you can't use to store as much energy in as small a space, but it could be a lot cheaper in the long run. And there's other technologies people are looking at kind of building on the lithium ion battery design, but trying to make it smaller and thinner. So that's more kind of for the consumer electronics direction. But one way you could do that is actually, so I showed a picture of a layered anode material, but one way you might be able to make that material take up even less space is by using just solid lithium instead of a layered material. But as Sean alluded to in his talk, there can be a lot of safety concerns with just using lithium on its own.
Are there other materials that kind of handle the thermal capacity of, the process of those batteries heating up? Are you thinking about what the materials, because right now it seems like what you're working on is having materials that allow that movement really easily, but what about that thermal aspect?
Yeah, so I think one really important question, like in a lot of kind of as we miniaturize electronics more and more, is how do we handle the heat dissipation for, also like in computers, for example, as chips get smaller and smaller. So there's a type of material called a thermoelectric material that that type of material is related to some of the layered materials that I talked about today. And basically a thermoelectric can convert a heat gradient into usable electrical power. So if you do have excess heat that's producing, you can, both take it away from your vulnerable battery and potentially convert it into usable power if you can somehow integrate a thermoelectric device into your system. So I think in general, like a lot of the materials we're looking at can have several different applications that are all kind of related to energy in different ways.
Yeah, and I think it's showing up on our Q&A. People are asking a lot about the safety of the thermal aspect, and I know Sean got that question too. So it's something people are interested in. So with that, I'm going to bring it back. So why don't we bring Sean and Jen back, and Lilia, you can stop sharing your screen whenever. There we go. So it's great to have you back, Sean. I know we have lots of questions coming in. This, like I said, this is a very timely timely talk. So Jen, do you want to start off asking a question to both of our panelists?
Sure, definitely. So I think this question may be answered best by Sean, but Lilia, please feel free to chime in as well. A few audience members want to better understand thermal storage, in particular, how you can deploy and transfer heat efficiently. So for example, does heat radiation deplete the energy storage over time? With regard to distribution, does storage need to be physically close? Basically, how is the heat transferred?
Yeah, no, those are great questions. And I didn't have time in the talk to get into what this would look like in practice. So the idea is if you are storing the energy with the intention of in the future providing it as heat, say to creating cement or glass or something, then you probably want that storage facility to be situated adjacent to your factory. You can get the energy there as electricity when there's too much electricity being produced. You then store it locally and then you can dispatch it as heat. Because it is very difficult to transport heat long distances. Probably the best way to do that and the way this would happen is with some kind of a fluid, which to engineers means liquid or gas, that would sort of pick up that heat and carry it over. However, if you wanted to later deploy the energy as electricity, then your storage facility can be adjacent to the electricity production. So next to your wind farms or your solar panels. Another advantage is that you can have sort of lots of modular small storage units distributed throughout a city. Which is in a sense also more robust against just disasters or if this part breaks, those parts are still working. And to the other part of the question, does radiation just deplete the heat really quickly? So we do have some thermal insulation around this. You should be visualizing in your mind these sort of big slabs of material, maybe tens of meters wide by half meter thick and 1 or 2 meters tall, kind of in a row, like sideways dominoes, but all of that encased in this big steel shell with pretty thick insulation around it. What's really nice, though, is that when you make these into large-scale structures, tens of meters across, your surface area to volume ratio goes way, way down. And the only way that you can lose heat is through your surface area, but you store heat in the volume. So it becomes self-insulating when you make these structures large. And that's a really interesting and beneficial result that people don't usually have an intuition for because we're used to interacting with everyday-sized objects that have thermal time constants on the order of minutes to hours. You put the turkey in the oven for a couple hours, but these things would take a really, really long time to cool off by themselves. We've estimated that the passive rate of loss of heat would be about 0.25% per day, which is actually better than some electrochemical batteries.
Thank you for that. Just sort of tagging onto that question, are there any cycling issues where, the temperature needs to be kept it needs to be kept at a high temperature to be effective, or can, the cycles of cooling, heating, cooling happen without issue?
Ask me in a year or two when we have more data. But the short answer is, so thermal cycling fatigue is sort of one of the biggest engineering challenges we need to overcome. The material would never be cooled all the way down. A fully discharged thermal battery might still be at 1,000 degrees C. So you're just cycling it between hot and very hot. But you are engineering your materials and your geometry to be maximally resistant to this thermal strains that you get from that cycling.
Got it. And I'm just going to tack on one more question from one of our audience members, and I think maybe both of you could answer this. Could flow batteries solve some of the issues with that interfacial heat buildup you mentioned?
So, okay, flow batteries, I am only loosely familiar with the concept. From what I've seen, they have quite a bit of potential in that they sort of distribute the energy storage through this electrolyte that gets pumped around. I don't know the technical details enough to answer yes or no, but I think they are very exciting. I think the biggest challenge with them, again, might still be cost for very large storage applications, but they might be an ideal sort of mid-scale technology. But I'm not an expert in those.
Yeah, I definitely agree with what Sean said. I'm not an expert in flow batteries either, but I think, so that's a technology that is kind of designed for a grid storage application and wouldn't be feasible at all in like consumer electronics or something on a smaller scale. So I think from the chemistry perspective, there's a lot of challenges in terms of making sure, the electrolytes, everything that you want to stay dissolved stays dissolved basically, and that there's no like side reactions that are taking energy away from the reactions that you want to actually convert your energy. But I think it's a very promising direction for like grid scale storage.
Thanks both. Dee, why don't I turn it over to you?
Sure. And the folks in the audience seem to know a lot about batteries. So this is great. Somebody asked, and Lilia, and obviously Sean, you can too, but can those graphite layers be doped with heteroatoms in order to improve lithium uptake properties? And I don't know what this means, so maybe you'll have to expand, Lilia.
Yeah, that's a great question. Okay, so graphite is just made of carbon in, the simplest case when it's pure graphite. So a heteroatom in this context means an atom that is not carbon. And so if you just basically like take a carbon away and put something else in its place, that will change the properties of the graphite. So one thing that it could do is kind of create a charge on the graphite layer if you replace the carbon with an atom that basically has like a different number of electrons. So I think that is a really interesting direction. I know that people have looked kind of in bulk battery materials, for example, like using graphite that has more nitrogen in it, for example. So I think that in some contexts can have better performance than just normal graphite. So I think that is a really good idea. And I think there are researchers that are exploring that direction. We haven't looked at it in these like 2D kind of sandwich, interface devices that I talked about, but that's a great idea.
Sean, anything more to add, or you're?
Nope, I think she covered it.
Okay, great. And a second question is somebody, we're thinking about energy storage and energy issues because we're really wanting a clean energy future, right? So what is the sustainability of the extraction of lithium? I know that's a concern too. So maybe both of you can speak to sort of the environmental impacts or the sustainability, because we're trying to make renewable energy. Is this renewable in a traditional sense?
Sure, I'll take a first stab at that. So yeah, this is a really great question. I guess there are two comments that come to mind. In terms of sustainability or impact issues of extracting lithium, as I understand it, cobalt is the sort of more ethically concerning element in batteries right now. Cobalt mining is not great the way it's done right now, and so there's a lot of effort to try to create cobalt-free batteries. But that's more on the concern of material ethics. In terms of sustainability, of like what are we going to run out of? Obviously, if it's a lithium-ion battery, you need lithium. And my answer to that is you can sort of look at fossil fuels to see the same trend. As the demand goes higher, the extraction techniques and technologies become more advanced. Fracking is an example of that now we've developed this fracking approach to extract natural gas. And so with lithium, I would suspect that if there's an increasing demand for lithium, we'll get better and better at extracting it from seawater, which is effectively an unlimited supply of lithium. Right now, I think it's too difficult to do, and hopefully whatever extraction technique we developed would not have, undesirable environmental impacts. So that's something we always need to be careful of. But I think, if the demand is there, it'll drive the innovation. And in principle, if you look at the oceans, we've got plenty of lithium.
Yes, somebody commented about kind of a sci-fi way to make batteries here in terms of biological batteries. I'm wondering if there's anything that either of you know about that sort of thing. So this is like mimicking the mitochondria for biological batteries. Have you guys, either of you, heard anything about that? Or?
So I think there's maybe like two kind of interesting directions that are related to that. So one is like, how do we make biocompatible batteries, and not necessarily using the same, machinery as biology uses, but how do we integrate, batteries as a component of bioelectronics that can kind of bring like, precision medicine in some shape to, everyone's like individual body. So I think people are looking at a lot of different like polymer materials that are biocompatible to kind of replace the very like non-biocompatible materials that are really common in batteries today. The other direction is actually related to flow batteries that we discussed earlier. So usually flow batteries the molecules that they use are also inorganic, so they have metals in them. But one direction that some researchers are exploring is replacing those with organic molecules that are easier to make and also less, like, they're less environmentally challenging to source, like the raw material.
Great. And just because we're on this sort of sustainability theme, I'll just ask one more question before I hand it over to you, Jen. In terms of recycling the lithium batteries, I know we had a question. There's so many questions here. You guys are amazing. It just said, what about recycling lithium batteries? So can you speak to recycling lithium batteries and what that might look like, and how, can we use those old batteries to make better batteries? Those sorts of in that area. What do you guys think?
Sure. So I cannot speak to the technological feasibility of the limits of recycling batteries. That's a bit outside my area of expertise, but I can again say that, economics is a very powerful driver. And if we end up in a situation where it's harder to get more raw materials, then there's going to be a drive to develop better recycling technologies, which hopefully we'll recycle just because we should for the environment, but failing that, the economic forces might bring that back around.
And I believe there are some, I'm not sure what stage these programs are in now, but there has been like pilot programs looking at, after batteries that are used in cars, for example, have kind of depleted their useful lifetime for being used in cars. Can they just be repurposed for grid storage projects, for example? So in that case, you're not recycling the raw materials, but you have a battery that still has, maybe 80% of its initial capacity. And so there are other applications that are potentially less demanding that maybe you could still use it for. But yeah, definitely, like, as the demand for storage goes up, then people will have more and more incentive to look at all of these alternatives.
That's great. Thanks, Lily and Sean. Sort of zooming back out to the big picture, we got an interesting question about the chart, Sean, that you showed early in your presentation about energy consumption. In the estimated energy consumption chart, it showed on the very right that almost 68% of energy is rejected. So the question is, can you explain and further comment on, is that inevitable? Is there always going to be that much waste?
Yeah. Someone has a very sharp eye. Yeah, I didn't go into that during the talk, but well, I won't pull up now, but yes, essentially, if you look at the full sort of life history of all the energy that we use in the country, where it comes in, how it's used, and where it ends up, about 2/3 of it is wasted, which sounds really bad. But a large part of that is thermodynamics fault, in the sense that there is a maximum efficiency with which you can convert energy from one form into another. That said, I wouldn't be able to quote numbers for you, but we can definitely do better than what those current numbers show. But a large part of it is inevitable. So we should work on it, but we shouldn't feel too bad that it's not at 100%, because that's just not physically possible.
Got it. Thank you for that. And then we've got a couple of questions for Lilia, I think. The sort of research you're doing right now to develop new layering technologies, what's the normal timeline or the time span between development of new layering technologies, like you talked about, and battery production lines? And as a follow-up, are the layers of other materials needed to make batteries less explosive or flammable? Can you talk a little bit about the safety aspects of that?
Yeah, those are great questions. So definitely the research that we're pursuing is at a pretty early stage, like it's very fundamental in nature at this point. So it is challenging to say, what the timeline will be, but like for it as an example, so graphene, which is one of the materials that we were looking as kind of one of the ingredients in these layers we're making. So that basically was like discovered in the early 2000s, and in the past few years, like I would say maybe the past 5 years or so, maybe past 10 years, there have been some like commercial products that now like contain graphene in them as one of the main components. So a lot of the individual like components of these layers we're making, the pipelines kind of to make them at an industrial scale are developing. So in that respect, I think like that definitely helps accelerate the timeline for our materials if they reach the stage where they could be used in applications. But yeah, I would say it's probably like definitely further out than 5 or 10 years. But then again, if something is really if something is really like a game changer, then that would probably accelerate as well. Just because if there's enough demand for such a technology, then it's going to be easier for the other pieces to fall in place. And the second part of the question is about the safety of the layering. So I think one interesting kind of side story with this discovery that I talked about, where we found that putting graphene with MOS2 allowed more lithium to go in than just MOS2. Well, it turns out if you just put lithium into MOS2, the material basically decomposes and like can start giving off like gases that contain sulfur, and that makes the whole battery expand. So we think that maybe if we can find the right combination of materials to put in these layers, you can like stabilize certain materials against certain processes in the chemistry. And so that's definitely like a direction that we would love to be able to address further.
Thanks, Lilia. It's great. I've got another sort of big picture question from the audience, which is that people are interested in understanding the difference in impact between, many homes who have installed batteries like the Powerwall versus large grid scale batteries. Can you talk a little bit about how those two sectors are both contributing to addressing some of the concerns we have around, climate change?
Sure. So impact in terms of like emissions and climate change in that sense.
Mm-hmm.
Yeah. So again, I don't know the specific numbers, but just I can give my speculation. My opinion is that the sort of smaller scale, home level storage, that should hopefully alleviate lots of little fluctuations of, maybe some person can have personal solar panels in their house and now they can store that energy. And so it's sort of a distributed collective effort to use less fossil fuels and be more self-reliant. And also that can help, for example, during power outages, if different houses all have their own storage capacity. So it can be very good for resilience as well. In terms of much larger scale, in general, technologies are cheaper when you make them very, very big. This is not an absolute rule, but that's sort of the general scaling. So I think we'll likely end up mostly getting the biggest win from those big scale grid level energy storage approaches. But I think having modular distributed energy storage can still help quite a bit for the transition when we're moving towards all renewable, and again, for the resiliency aspect.
That makes sense. Thank you.
Great. So I love this question because it incorporates an analogy. So, and I think this question came in when Sean was speaking, but I was thinking about it when Lilia was speaking. So it's really applicable to both of you. So the question is, I'm always amazed by the precision and the resolution of the instruments and the sensors you must be using to do this work. So I know the sensors, right, Sean? And then, I mean, you must be in a clean room, Lilia. Like, how are you even, like, it's an atom thick layer. Like, how does that even work? So the question is, can you tell me if, how can you tell if you're at the spot in the sample that you want to be? How can you measure, how can your measurement be so precise? I'm thinking about playing C on the violin. Maybe it's a C, but more likely it's just really close to a C, right? You don't ever really know if you're hitting C. So how do you guys know that you're doing what you think you're doing when you're working with in such a small space?
Sure. Okay, I'll go first, and then I'll let Lilia talk about literal atomic scale manipulations. So in our case, there are lots of very clever tricks that people have learned over time they can play to get very precise measurements. So it's really, science is continuously building upon itself. So our techniques are building on modifications of other techniques that are being proven, which themselves were built on other techniques. And so we pass down these tricks. So one example, without getting into too much of the weeds, I mentioned that we send out these thermal waves. And so this is what's called a frequency domain measurement. And so we will measure the signal at a particular heating frequency, maybe 10 hertz, maybe 100 hertz. And because the system responds linearly, that means if you excite it at a certain frequency, the response is that frequency. We can listen in at exactly that frequency. For the technical people in the crowd, you can do a Fourier transform and pluck out that Fourier component. But it basically means that we can reject tons and tons of background noise. So our signal to noise ratio in terms of separating the thing we're looking for against all the noise is about 6 orders of magnitude, meaning we can have a signal that is 1/1,000,000th as strong as some of the background noise and still get it very reliably because we do this frequency lock-in approach. And that's something that we've learned from other people. And there are many similar type approaches. And I'll let Lilia speak to her system.
Yeah, well, I think I definitely have to say that in my experience, what Sean said about there being a lot of kind of tricks that are passed down, through the ages is definitely very true. But I think there is also, well, one thing is that there is, when you're making these, atomic scale devices and things, there is a certain level of just like probability in terms of like how many of the devices might fail, that you just might not, get what you wanted to see. And so I think in general, like when you're looking at presentations from like scientific presentations, it's not, most of the experiments have probably failed. What you're seeing is like the successful ones. So it's not like, it works perfectly every single time. And there's a lot of kind of just like statistical, like, sometimes you just lose like what you were looking at and you can't find it again. But there are, people have developed like basically better and better microscopy techniques that really allow us to do the work that we do. And so electron microscopy is really important. So the idea there is that instead of using light to look at your sample, you instead use a beam of electrons. And basically these electrons have like a much smaller wavelength than light does. So your resolution is much, much better. And so with certain techniques, you can even see like the individual atoms in your sample. And so you can really get a very good picture. Like if we have to make like macroscopic devices just because we're people and that's what like we can handle with our hands. But if you can find, like what you made, you can really see the individual atoms if you can use like these advanced microscopy techniques. So that's really like what makes all this like nanoscience, nanotechnology work possible.
And I'll actually quickly add one more quick point. I think she made a good point that the yield is often low and you have to repeat things many times. So whenever you see experimental data, there's going to be some kind of an error bar on it. And so there's always some distribution, some standard deviation, ideally repeated measurements. So back to I think it was a fun analogy, if you just had to play C on the violin one time, you might be off by a little bit. But if you played C and then you retuned your violin and then you played it again and you repeated that process 1,000 times, and then you averaged all of those 1,000 trials, the average would be very, very close to a perfect C. And so that's another property that we can exploit, especially for quick measurements, is just gathering lots of statistics and building confidence.
I love bringing it back to the analogy. You can use that now, Sean, when you... Okay, so are there this is a great question, I'm curious too. Are there commercial examples of heat energy storage systems that either of you can point the audience to? I assume this might be more appropriate for Sean in that sense, just because you did talk about a lot about the heat energy system. So there seems to be plenty of lithium-ion utility scale projects. And I know that many renewables companies are investing heavily in battery storage projects, but I haven't seen any heat storage projects. So the question is, do they exist, and can you point, consumers to those projects or to those products?
Sure. Yeah, great question. Yes, there absolutely are already commercial heat storage technologies out there. The reason you're probably less familiar with them is that they tend to be, again, for much larger scale storage applications, which tends to be more steps removed from the individual user. We're more likely to interact with batteries because that's in cell phones. But to list a couple examples, one big one is molten salts for concentrated solar power. So if you've ever seen these like concentrated power towers, it's the big tower, looks like Eye of Sauron glowing at the top and surrounded by all these mirrors. They're trying to integrate thermal energy storage with those. They've deployed some where they melt salts. So that's around 600 to 800 degrees Celsius. And that acts both as a heat transfer fluid and to store energy for when it's nighttime. So that solar power can still supply energy at night. And then you also see on the other side of the temperature scale, some deployed technologies for cold energy storage. So the idea here is, let's say you're trying to control the environment inside of a commercial building, and it's really hot, some summer climate. You don't want to run the AC ideally in the middle of the day when electricity is most expensive. So what you do is throughout the night, you use that cheap electricity and you freeze water into ice. And then during the day, you can sort of pump water pipes through this block of ice to cool them off. And then you use that and you recirculate it into the building to cool the building. And so you can kind of store cold energy in that sense. And I don't remember the names of the companies, but this is being deployed in certain places as a cheap form of heat storage. What we're focusing on mostly is high temperature energy storage. That's why we need sort of new research there. There are a lot of potential benefits for the higher temperatures, but there are also some challenges to overcome. Antora Energy is a startup company here in Berkeley that I work very closely with, who's really pushing forward on this.
So I've got a couple questions coming in, a little bit more about your research specifically, Sean, around the sensors that you've established. So the question is, are the sensors heat flux sensors? And if you could you please describe the sensing mechanism in a little more detail and comment on the effect of wiring on measurement accuracy? So thank you for that technical question.
Here, let me do this very quickly. One moment. Share screen again to just show this slide, I think will be helpful. So the idea here is you have this sensor and you put it on top of a multi-layered battery stack. And as I said, we then periodically heat it. So it acts both as a thermometer and a heat flux source, so not a heat flux sensor. And the idea is you drive it through multiple different frequencies. And those high frequencies will produce thermal waves that only penetrate shallowly into the battery. And then you record the temperature response on the surface. And then you go to lower and lower frequencies. And at those low frequencies, the thermal waves can penetrate deeper into the battery. And so what you're really doing, again, for the technical people in the audience, is you're characterizing what's called the thermal transfer function of the battery. And so even though the sensor lives on the outside, fundamentally it's detecting a temperature oscillation on the surface of the battery, but it can relate that surface information to thermal transport properties within the battery by sweeping over different frequencies, because different frequency waves will penetrate to different depths through the battery. So hopefully that gives a little bit more sort of visual intuition for what's going on.
Sorry, thanks, Sean, for that answer. Another question about your research. Somebody asked, what size of graphite particles are required for efficient heat storage? And is solid carbon or a carbon composite more efficient at storing heat?
Great questions. So solid particles, there's a form of energy storage discussed called falling particles. And the idea here is you have quite small particles, smaller than a marble, bigger than a grain of sand. And you kind of carry them up in a conveyor and then you let them free fall down as concentrated sunlight hits them and heats them up. And you kind of recycle them this way and then you store the energy as heat in those particles. And that is definitely a viable approach. And Cindy and some other folks are looking into that. What we're looking at is a slightly different form of solid thermal energy storage, which is one large chunk, well, multiple chunks, but large chunks of graphite. Again, you can visualize something on the order of 1 to 2 meters tall, maybe 30 centimeters thick and up to 10 meters long. So big, big blocks. And there you want something that has a high thermal conductivity, which means it's easy for heat to flow in and flow out quickly so that you can get the heat from the middle of the block out to the surface very easily. And to the other part of the question, so composite materials will almost certainly give you better material properties, but they might also be more expensive. And so we have a research project we're just starting now to kind of try to optimize all these competing factors of making material that's, very thermally resistant, very thermally conductive, also very cheap, very abundant, safe, all these kinds of things. And we're going to see if we can come up with a sort of perfect storage material in that sense.
Thanks, John. Let's see, we've got a few more questions from our audience. Let's talk sort of big picture again. A few years back, one of our attendees heard about batteries which can be charged really fast, like in a matter of seconds, and then discharged over longer periods. These are two kind of separate paths for charging and discharging cycles without overheating. Could one of you talk about where that technology might be now? Is that feasible? Is that something that we can expect to see in the next couple of years?
So yeah, Lilia.
I'm not sure if I've seen this exact technology that this audience member is talking about, but there are devices called supercapacitors that I think I mentioned in the response to Dee's question, but these can basically charge really quickly. And there's a lot of commercial applications for supercapacitors today. So they're used in wind turbines, for example. They're used in some like pretty high-end hybrid vehicles because they can provide like a lot of power really quickly. But they generally don't have an energy density that's as good as batteries, so they can't provide as much energy or as much power over time. So perhaps something like a hybrid between a battery and a supercapacitor could approach that kind of best of both worlds scenario. But unfortunately, yeah, I'm not sure if we have anything like that on the market today.
I don't really have anything more to add. I agree that there's a lot of different exploratory paths right now, and hopefully some of them will work. But I'm not sure specifically which chemistry that audience member was referring to.
Great. So do either of you want to talk about, or maybe Lilia, as it relates to creating new batteries and new battery design, want to talk about the green chemistry aspect and how this plays into your role when creating and focusing on new batteries? Are you working with green chemistry folks? And if you could, maybe other audience members might want, like, green chemistry, what does that mean? So can you speak to that also?
Yeah, so to my understanding, green chemistry is just generally the principle of trying to move chemical processes into like a more sustainable direction. So like usually specifically about using just more sustainable starting materials, like materials that are more easily sourced, and not depleting limited natural resources. So I know Sean mentioned earlier that cobalt is a really big challenge, especially for lithium ion batteries. So I believe like the batteries that are in our smartphones, for example, the majority of the metal in the cathode is cobalt. So there's a lot of challenges around cobalt mining, and definitely one direction that would be really would help green the entire lithium battery industry is if we can develop an alternative to cobalt. And even in like electric vehicles, for example, or like larger batteries, there can be a lot of cobalt in those batteries as well. In terms of other chemical designs, I think in general, moving away from like precious metals is always very important, a very important direction. So I didn't talk about fuel cells at all today, but that's basically a type of, it's not really like a battery, but essentially you can convert hydrogen into usable energy, and it doesn't use any fossil fuels. But the catalyst that performs the most important chemical reaction in a fuel cell is usually based on platinum. So a lot of researchers in chemistry are looking at how we can replace that platinum with metals like nickel or iron, which are just much more abundant.
Yeah, and there are other issues with fuel cells, right? I'm sure you both.
Yeah.
Just like, aren't those the ones that you can't use like when it gets really cold? Is that what the fuel cells, they kind of break down?
I'm not as familiar with fuel cells. I know that they usually operate fairly hot. I think sometimes even hundreds of C. Batteries actually also can have problems when it's really cold, but I think they're not quite as temperature sensitive.
Okay, so we have two more questions lined up. So our second to the last one is, does lead acid have a place in utility scale storage? I see UCLA is doing nano studies in this old technology. So bringing back an old technology and trying to figure out if it scales. Do you guys have any information or knowledge on that?
So to my knowledge, I don't know a lot about this area, but I think a lot of, so in terms of like different energy storage technologies, they have different like kind of rates that they can provide power. You know, they have different power like ratings and different like energy ratings. So there's often like a compromise between, you know, the amount of power they can provide, the amount of energy they can store, and of course the price. So lead acid can't store a lot of energy in terms of like the volume it takes up and the weight of the battery, but it's very cheap and it can supply a lot of power pretty quickly. So situations where that's fine, the lead acid is still pretty widely used today. So I believe a lot of like uninterruptible power supplies, for example, those will still use lead acid. So it's more of a short-term application. So they're only discharging for like on the order of minutes, probably, not hours.
So less scalable then.
Yeah, I would say so.
Yeah. Sean, anything to add?
I think I would just sort of amplify what Lilia said, that
Yeah.
there's never going to be this one perfect battery chemistry. It really depends on your application.
Yeah.
Different applications have different trade-offs between their criteria.
Right.
So, you know, large scale stationary storage, it's okay if that battery is really, really heavy, as long as it's cheap. But if you're trying to put batteries to power a drone, you want it to be really, really light and you know, power dense, even if it's a bit more expensive. So even for that reason alone, it's worth pursuing a few different approaches for different applications.
That seems to have been a reoccurring theme between both what you and Lilia have to say, right? It's application and how you're using it. So our last question is a fun one. Jen and I decided to go off with another a bang. Can you speak to the potential of dark matter as an energy source?
Dark matter. Well, I'll be able to speak more to it once we know what it is. Yeah, I mean, I guess there's a lot of energy in the universe, the majority of it actually, that we haven't tapped into, and that's, you know, actually dark energy, which is a different thing from dark matter. I suspect that that's probably not within the next 2 to 5 years. But, you know, if we ever did figure that one out, that might help us, you know, visit some other planets.
Well, when we're able to live till we're like 120, we'll bring you back in, you know, 80, 90 years to have you talk more about that. Lilia, anything more to add?
No, I mean, that would be great if it happens in the future. I'll have to learn about it.
Okay, I think maybe you can count on Berkeley Lab and UC Berkeley to be at the forefront of those discoveries when they happen.
All right. Well, we have had so much fun with you. We have had such a lively conversation. We had a record-breaking number of audience members. So thank you so much to our audience for coming, tuning in, and we'll be back next month. Jen, anything more?
No, thanks so much. We're glad you joined us. We really appreciate the presentations from Lilia and Sean. And as Dee said, we appreciate you tuning in. We'll see you next month. Thanks, everyone.
Thanks everyone.
Thank you.